just wait. All right, let's start. So today we are going to learn a new type of testing technique called mutation testing. It is actually quite special. We will see that later. And this is today's outline. So we will first learn and have an overview of mutation testing, and then we will learn some important concepts of mutation testing, like the mutation operators, like how do we conduct mutation testing. And lastly, we will talk about how can we combine mutation testing with fuzzing or fuzz testing. So before we jump into the main content today, it's okay. Let's have a look at the last question of assignment 1. This is the source code of the last question. So it's basically the function that could find the maximum value of 3 integers. So the first question is, for this program, can these 4 test cases achieve full path coverage? And let's have a look at how to solve this problem. So this is the control flow graph of this function here. You can merge this node with this one here, but you should keep your control flow graph consistent in one CFG. So so let's continue. This is a CFG, and we can see that we have 4 paths for this program. And let's consider the first test case. So the first test case, if we go to the first, if we encounter the first if condition here, which branch will this first test case take? The true branch, right? The true branch. And then the temp value equals to A here is assigned to A. So temp is 4 and C is 5. So C is larger than 4. And we will take the true branch of the second if. So this covers this path. And let's consider the second test case. So it will also take the first true branch. But this time C is smaller than 4. So we take the false branch of the second if. So this covers this path. And for the third test case, A is smaller than B. So we will take the false branch of the first path. And then we will, because C is larger than 3 here, temp will equal, if we take the false branch, the value of temp will become the value of B here. So C is 4 is larger than 3, so we will take the true branch for the second if condition. So this is the third path covered by the third test case. And the last one here, we will take the false branch as well. And then because C is 1 is smaller than 3 here, so we will take the false branch of the second if condition here. So we can achieve full path coverage for this with these 4 test cases. And remember, in the assignment, we have an open-ended question, which is to modify the original code to inject a bug, a logic bug, which cannot be discovered by these 4 test cases. And we can actually use change just one line to achieve this. And one of there are many possible solutions, and one of them is to just modify this first if condition here. So we can change it to from A is larger than B to A is larger than B plus 1. And let's consider the test cases again. So for the first test case, 4 is larger than 2 plus 1. So we will still go to the true branch. And And the temp value will become A here, and 5 is larger than 4, so we'll take exactly the same path for test case A, for the first test case. And for the second test case, it is also the same here. So it will also take the previous path. And for the third one, it is still the same. And it's also the same for the first test case. So our existing tests can still pass if we do this modification. And the question here is beyond these assignment questions. So can we come up with a test case to capture this bug, to capture the injected bug here? So one of them can capture this bug here. So let's do a live poll and see if you can identify which test case can uncover this change here. Just a hint, if the test case covers the same execution path in both programs, it won't be able to find the bug. If it triggers a different execution path in the buggy program, it will be able to help us to find the bug. So which test case can capture the injected bug? Okay, we have 4 answers and we have 4 students. So the test case 4 is the correct answer here. So let's have a look at why test case 4 can help to uncover the bug. So we can quickly exclude test case 1 and 2 because they don't affect, and they are not affected by the change, because A is already smaller than B. And if we change the condition to become A is larger than B plus 1, both test case 1 and 2 are not affected at all. So the tricky part is how do we differentiate test case 3 and 4. So first, let's have a look at why test case 3 cannot help us to identify the bug here. So actually, the original program is to return the largest value among A, B, and C. Let's remember this. So this can help us to easily understand what it should return. So for the test case 3, because of the semantic of this program, it should return 4. And let's see what happens. So in the original program, 4 is larger than 2, so it takes the true branch for the first if. And C is smaller, 2 is smaller than 4, so we'll take the second if branch, the second if condition with the false branch here. So this is what happens in the original program for test case 3, and we will return 4. We will return 4. And for the buggy program, A is 4. 4 is larger than 2 plus 1, so it will still take the true branch here. And 2 is smaller than 4, so we will still take the false branch here, and we will still return 4. So imagine we can add an assertion to check the return value, whether it equals to the largest number of A, B, and C, and this will not be able to find the bug here. However, if we use test case 4 here, what will happen is, in the original program, A is larger than B, so we will take the true branch of the first if condition here. And then, because C is smaller than 2 is smaller than 3, so we will take the false branch of the second if. So this time it will return us 3. It is the correct answer. However, if in the buggy program, because this time we modify the condition here, so 3 is not larger than 3. 3 is equal to 3. So we will take the false branch of the first if condition here. And then this time, the value of temp will be assigned with the value of b. So temp equals to 2 here. And because the value of c is exactly 2, and 2 is not larger than 2, so it will take the false branch again, and it will return as 2. So we can see that we can find the bug here. Assume that we do an assertion to check the return value with the largest value of a, b, and c. So we will find the bug with test case 4. So why do we need to revise this assignment question? So it is actually related to today's topic. So what kind of observations can we make here? So the first observation is that we need to be aware of not just the control flow, but also the data flow. Because with the previous 4 test cases, we can already achieve full path coverage. We can already cover every path in the control flow graph, and there are still bugs which could not be detected. So we need to be aware of data flow. Although data flow is not one of the key topics in this course, but it is actually still important here. So you just need to know this. And the second thing is boundary value testing indeed helps. So this is not exactly the black box boundary value testing, but if we write test cases, we should consider to use values closer to the boundaries. And we will need to think about, because test case 4 is actually better than the previous test case 4, right? So how can we evaluate the quality of a set of test cases or a test suite? So this is the question here. So we can build better test cases, but how can we determine if a test case is better? So this comes to the topic of evaluating test cases. Previously, we know that we can use test cases to evaluate the target programs, and we need something to evaluate the test cases, and we need something to evaluate that thing. So this leads to a recursion. But there's actually not a recursion here. We don't need to evaluate everything. So the thing is, test cases and target programs should be treated equally somehow. And we can use test case to evaluate target programs. So we can also use target programs to evaluate test cases. So we can create some target programs to evaluate the test cases here. And this comes to mutation testing. So the mutation testing, the key idea of mutation testing is to modify the original target program to create mutants to test the test cases, to evaluate the test cases. And you can see that there's a keyword mutant here. And this word is borrowed from biology, which refers to a small variation of the original organism of whatever thing. And if you have played the game of Resident Evil, or if you have watched the movie, you will know that these are some mutants, biological mutants. And the thing is, if a test case can capture a bug or the modification we have made to the mutant, it is said to be able to kill that mutant. So test cases could be considered as the main characters in Resident Evil, and they can kill the mutants. And if a test case can kill mutants, then it is normally considered as a good test case. So that's just some informal definition, and let's come to some formal definition of some concepts in mutation testing. So first, the mutant of a program is actually considered as the result of making a small change to the source code of the original program. So normally the change is very small, and we only do one change per mutant. And the second one is a mutant is said to be killed if for at least one test case the execution it can pass that test case can pass the original program, but it doesn't. The mutant cannot pass that test. So it is in this case the mutant is considered to be killed. And if a mutant can pass every test case, then this mutant is considered a live mutant. And if we divide the value of killed mutants with the value of total mutants we can have the mutation score. So this mutation score is actually the score for the test suite. And let's come back to mutation testing. So how does the umbrella company create mutants in Resident Evil? So they actually use some kind of virus called T-virus. And here, how do we create mutants for a program? So we don't use viruses to create mutants for programs. Instead, we use mutation operators. And that leads to the second topic today, mutation operators. So there are some key characteristics for mutation operators. So first, these mutation operators are intended to model common types of errors or faults. And the second characteristic here is it is normally designed to be applicable to any code, any type of code automatically. And then the last one is most of the mutation operators tend to be some simple syntactical faults. So normally what we can do is we can replace one variable reference with another one. We can change the comparison from smaller than to smaller than or equals to. And we can also reference a parent class instead of a child, do some small changes like this. And here are some more detailed designs for mutation operators. So it's from the bottom, from the small components of the code to some larger components. So the smallest building part, building blocks of programs are operators and operands. So what we can do is we can modify the operands. So the first type of operand mutation operator is called X for Y replacement. So what we can do is we can replace one constant with another constant. We can replace a constant with a scalar variable. So what is a scalar variable here? So a scalar variable is in contrast to a vector or an array. So a scalar variable actually is a variable that refers to a single value without complex structures. So we can also replace scalar variables with constants. We can also replace one scalar variable with another one. And we can replace a scalar variable with an array reference, because an array reference refers to one particular value. And we can also do it reversely. We can also replace array reference with another array reference. And by doing this, it means that we can either change the array, the pointer to the array, or the array index with the same array. So we can do all these type of changes for operands. And with operands, we can also do, and we can also change operators. So for arithmetic operators, there are some binary operators, like all these arithmetic ones, and there are unary operators, and there are also some shortcut operators. So what we can do for mutation is we can replace arithmetic operators. So we can replace these operators with one another. We can replace shortcut mutation operators with unary operators. This will simulate some cases where the developer may make some typos. Sometimes developers could forget to type 1 plus sign here or 1 minus sign here. So this is about arithmetic operator replacement. And what we can also do is we can do arithmetic operator insertion. So we can insert an additional operator into an expression and see what happens. What else we can do is we can also try to do it reversely. We can also try to remove an arithmetic operator. We can delete one from an expression. And there are more expression modifications we can do. So the other type of operators are conditional operators. So for conditional operators, we could have binary condition operators, which are all the logic operators. And normally means logic and this is logic or, and this is bitwise and this is bitwise or, which means that we perform we calculate the value of the value of the OR of every bit of x and y and put it in the result. And this is bitwise XOR. And for unary operators, we can have not. This is not, and this means bitwise negation, which means that we are flipping the bit of x here. So we have these conditional operators, and what we can do is, and also we also have some relational operators. So these are normally used in conditions, and we also have shift operators in some programming languages. So this is to shift right by one bit, by certain bits. So this is shift left. And shift right and left means in binary means multiply or divide. So these are the shift operators. And what we can do is very similar to what we can do for arithmetic operators. We can do replacement, we can do insertion, we can do deletion. And there are more operators. We do have some shortcut operators, which is to calculate the value and assign it to x. So these are the shortcut operators we have. And we can do similar things with the shortcut operators. And there are some more modifications we can do. We can try to replace a sub-expression in one expression with some absolute values. And we can try to replace a predicate, because for those relational operators, they are normally used in predicates or conditions. So we can replace the value of the entire predicate with a constant value of true and false. And that's all about expression level of mutations. So now let's move up one level. Let's come to the statement level of modifications or mutations. So the first thing is we can do statement deletion, which means that we can remove a random statement from the original program. And we can also try to replace switch cases. We can replace the case with a predicate of the case with a constant true and or false value. And we can also shift the end block. So because most of the code blocks are are wrapped by brackets, and we can move the closing bracket to an earlier or later location to enlarge or shrink the size of this code block. So this can also do some variations here. And what we can also do is, that's all about statement level. And I believe all of you have learned about object-oriented programming. And there are some key concepts in object-oriented programming. And one of them is called encapsulation, and the other one is called inheritance. And we also have polymorphism. I hope you can still remember them. So let's move up let's move one level up from statement level of mutations. So what we can do for a higher level of mutation is we can try to modify the access modifier of an OO language. So for example, in Java, there are some modifiers called public, protected, and private. So we can change the modifier from public to maybe to private or protected, and see what happens to the program. So this is related to encapsulation. And we can also try to do hiding variable deletion. So the concept of hiding variable is a variable in the subclass that has exactly the same name and type as a variable in the parent. So it is actually hiding the variable of the parent. So it is called a hiding variable. What we can do is we can delete the hiding variable in the child. And the effect of this is to cause, because when we use objects of this family of classes and access that variable, if we delete the hiding variable in the child, instead of accessing the variable of the child class, we are actually accessing the version in the parent instead. And this actually simulates how the developers may forget to implement a hiding variable in the child class. So this is a very small change in the program. And we can also try to insert hiding variables. So you can see most of the mutation operators, they have a mirror of one another. So for deletion, we can also do insertion. So what we can do is we can insert a hiding variable into a child class or into a subclass. And the effect is that instead of when we reference a variable through an object of this family of classes, we are, instead of referring to the variable in the parent class, we are referring to a variable in the child class. So these are some mutation operators we can do for encapsulation and inheritance. And for inheritance, we can do more mutations. So the first one, the other one is Uh-huh.
So when would you actually have test cases that fail on like public-private modifier issues?
Oh, you will. Yeah, that's another thing. We will need to have a look at it later. But if we are restricting the access, like if we change from public to private, we may fail to compile the program if we try to use maybe a public method from another piece of code. But if we are losing this restriction here, like we are changing from private to public, and we somehow accidentally write some code to access this method here, then the program behavior will change. So that's how a test case would capture this. Yeah.
It seems like it's quite hard to test all those things, right? Because you have like a single program, you have like hundreds of these modifiers.
Yeah, that's.
People actually end up testing whether things are visible.
Actually, that's the viability of mutation testing. We will learn it later today. Yeah, that's a good question, actually. That's a practical issue here. And let's continue to learn this mutation operator. You don't have to remember all of these. These are some just boring concepts. But I still need to introduce this to you because you need to have a brief idea of how to do it. And all these slides could be used for documentary purpose. So let's continue. So for overriding methods, can you still remember the concept of overriding methods? So can you still remember that? Okay, good. So what we can do is we can delete an overridden method from a subclass. So overriding methods means the method in the subclass has exactly the same signature as a method in the parent class. So we can delete. This is very similar to hiding variables. So we can delete it. So if we delete an override or an overridden method in the subclass, all the references to the method will be calling to the parent. And we can change the calling position of these overridden methods. And there are some other things related to inheritance. For example, the super keyword. So the super keyword is actually used to access parent elements from the child class. So we can try to insert or delete the keyword within some methods. So, and we can also try to rename overridden method. So we can also try to do explicit parent constructor call deletion, which means that in some constructors of a child or subclass, we need to invoke the parent class using the super keyword, and this actually helps to initiate some variables in the child class, and so this can actually help to capture some errors or bugs with initialization issues. And the last concept of mutation testing is called polymorphism. So we can also do modifications or mutations related to polymorphism. So what we can do is we can do a new method call with child class type. So we can replace a declaration with a valid child instance. So polymorphism means that one superclass could be inherited by several child classes, and if we try to ask an object to do something, instead of using the method of a particular child class, we can use the method of a parent class. For example, we can have animals, and cats and dogs are subclasses of animals. And instead of just ask, we can write a piece of code to ask an animal to run, instead of asking a dog to run and asking a cat to run differently. So this can help us to save some coding effort. So this is the power of polymorphism, and it is mostly related to having multiple child classes inheriting the same parent class. So what we can do is, because we have multiple child instances for one parent class, we can replace the child instances with one another. So we can do this. This is just an example here. And another thing we can do here is we can declare the variable or parameter type with the parent class type. So maybe instead of declaring a new cat or a new dog, we can just declare a new animal and see what happens. So this is polymorphism modification, and we have more mutation operators. So we can do type case operator insertion or deletion. This means that we can actually change the reference to a child type and cast it to the parent of that child. So for example, or instead of calling maybe a cat to string, we can cast the cat back into animal and then call the method. Or we can delete, or sometimes we may do, there are some castings already in the code in the original target program. We can also try to delete these cast operators. And we can also try to change the casted type. It's somehow similar to how we replace one child with another valid child. So instead of casting the object into a particular child, we can try to cast it into another valid child here. And we can also try to do reference assignment with other compatible types. So we can change an object reference with a pointer pointing to some other compatible variables. And this is somehow very similar to how we can do the child class or the child reference replacement. And apart from overriding, we also have the concept of overloading in object-oriented program. So do you still remember the concept of overloading? Okay, good. So overloading actually means that we allow two or more methods to have the same method name if they have different signatures. So this is very useful if we try to if a function if a particular feature should accept different types of inputs, but it will do the same. It will have the same effect. So this is very common in Android programming, and overloading method contains change. This is the first mutation operator we can do. So what we can do is we can replace the body of the we can replace the body of those overloading methods with one another, and we can also try to delete one of them and see what happens. And we can also try to change the arguments. Instead of just changing the body, we can change the arguments. So do you have any question here? Yeah, that's another case. But sometimes it could compile, sometimes it couldn't. But it depends. And that's another practical issue. And we should build compilable mutants, and let's see later. And that's it for the first two topics. And let's have a 10 minutes break, and I will see you at 2:53.
Do you mind if I just ask some questions?
because it's running very fast, and it's running out very fast. What you can do is you can try to add a sleep here when each time you execute the target. So you can observe the log easier. You can like sleep for 1 second.
I haven't looked at this too much. Well, actually, like, you look at the printout
yeah.
as well. And
Yeah, you can look at the printout.
Okay. Let's see how that looks.
I actually added a way to just break out of the loop if there was any kind of status code that wasn't 0 and it just kept going forever. So I guess it's not very good at doing anything.
It's acceptable actually. Yeah, because some files in some implementation of files, they will break out the file once it finds a bug.
Okay.
So that's doable, but not for this one.
Yeah. Okay.
You can add a sleep here to make it run slower.
Yeah, I'll have to figure out what you guys are talking about.
It's better to start early for this one because for the last assignment, I think most of the students don't start until the last 2 or 3 days, so it's a little bit of rushing. And you can finish this one in 2 or 3 days, I think.
How long do you think it would take to finish this assignment?
Maybe 1 week. If you are good at coding. So I try to make most of the content related to what has been taught before week 7 or this week. So you don't need to rely on the new lecture contents to do assignment 2.
I actually just had a different question about House's metrics from last week, I believe. Is there like a consistent list of what counts as an operator in House's metrics? Because I've seen some where they count even like brackets and parentheses, but that's not counted on the lecture slides.
Actually, I don't suggest to count brackets because house type matrix is a very old metric, and it was proposed in 1970s. And by that time, the programming language were very low-level languages, like assembly language. And for assembly code, if we compile, because most of the C code or even Java code, Java is compiled into bytecode running in GDM. And for assembly code, we don't have brackets at all. So most of the assembly code are the operators and operands are very clear. So you can see here, all the left-hand side are the operators and all the right-hand side are operands. So all of them they don't have brackets here.
Yeah.
So that's why I don't think it should be considered. Yeah. But if it is a bracket for accessing an array element, then it is considered as an operator. Because it's more like, you see this bracket here, it means accessing a particular memory address. So this is an operator actually. All right, let's continue today's lecture. And if we have some time after covering all the lecture slides, we can talk about assignment 2 as well, how you can do assignment 2. And we have just learned an overview of mutation testing, and it is a special type of testing to evaluate other testing techniques or test cases. And we have learned the key concept of mutation operators. And now let's see how do we conduct mutation operator in practice. And there are some problems you have proposed. And the overall workflow is like this. So first we need to select mutation operators that are suitable for the code. So because for just now we learned some object-oriented mutation operators, and they are definitely not applicable to C code. And for the second step in the workflow is to generate some mutants by applying mutation operators to the program, so we can generate a lot of mutants. And the last step is that we can execute the same tests of the original program and mutants to kill the mutants. And the definition of killed is just following the previous formal definitions. So these are the three steps in doing mutation testing. And of course, the more mutants killed, the better the quality of the test suite is. So just now you talked about viability of doing mutation testing in practice. And actually, most of the mutation operators reflect small syntactic mistakes. And programmers do make such mistakes, but many of the faults are actually conceptual or logical mistakes, not just some very simple syntax mistakes. So maybe the programmers may make some false assumptions about the requirement. Maybe they forgot about certain requirements. So the question here is mutation testing a viable technique? And the answer is yes, in some conditions, under some assumptions or hypotheses. So mutation testing is valid if the seeded faults could represent real faults. And we do have a hypothesis here. So because normally we don't assume we should assume that the system under test or the program under test is close to correct, so they don't have big mistakes like missing some requirements or some wrong understanding of requirements. So we assume that programmers are very good at understanding those big concepts, and they only make small mistakes. So this is the first assumption here. And the second key thing here is called coupling effect. So many faults are actually small syntactical errors. And you could consider them as syntactical errors, because if you do lead code, for example, the trickiest part is should I plus one, should I not plus one, right? Should I use larger than, or should I use larger than or equal to? So there are some borderline cases. And those are logical faults, but they look like small syntactic faults. So, and if we build larger faults, if we want to build larger faults, we may use some and if we accumulate these small syntactical faults, we may end up in some more complex and larger faults. So the coupling effect hypothesis is complex faults can be modeled by a small set of small faults, a set of small faults, and a complex change to the program is a series of small changes. So if one of the small changes is not masked by the effect of other changes, then a test case could notify the small change, can also reveal the complex change behind this small change. So this is the coupling effect. So coupling means small changes and complex changes is coupling. They are coupled. So mutation testing is effective if both the competent programmer hypothesis and coupling effect hypothesis hold for the target scenario. And we also need to care about the quality of the mutants when we do mutation testing. So to be used in testing, the mutants must be valid, so which means that they must be compilable and they must be executable. So if we, for example, if we do some random mutations, we may end up in breaking the program and making it not compilable. Then that mutant is not considered to be used at all. So, and we do have some, because all the mutation operators are some very small rules and they could be easily automated. So we can easily use some other scripts or some programs to build a large amount of mutants and try out and try to get the valid ones. And the second property is the mutant must be useful. So it must provide some useful information about how the system works. And so the question is, can a mutant be valid but not useful? Yes. And let's consider why a mutant is still live, because the liveness of mutants could be used to evaluate the quality of the test suite. So if the mutant is semantically equivalent to the original program, because sometimes when we do a small change of the program, it doesn't affect the semantic of the program at all. So they are equivalent to the original program, and in this case, the mutant is considered valid but not useful. And of course, the liveness of mutants could be used to evaluate the adequacy or the quality of the test suite. And the test suite is inadequate for that mutant sometimes, which means that the quality of the test suite is not good enough. For example, for A smaller than or equal to B and A is larger than or equal to B cannot be differentiated. If we change from this one here to this one here, and in our test case, A equals to B, then the test case cannot kill this mutant. So, and just now we also see from the very first example from assignment 1 that some test cases couldn't be used to kill the mutants at all. So that's why, from the live poll, only one of the test case could kill that mutant. So the small changes can reflect the quality of the test suites. So yeah, that's about the case study at the start of today's lecture. And let's talk more about mutant score and coverage. So just now we learned the concept of mutation score in the overview of mutation testing. And it means that this mutation score can be used to measure the quality of a test suite. So the higher the score is, the better the test suite is. So it means that the test suite can kill more mutants. And mutation coverage can subsume some structural coverage metrics we have learned in lecture 5. For example, mutation coverage can subsume statement coverage, because what we can do, let's think about an extreme case. We can apply statement deletion to all the statements, and to kill a mutant for a particular to kill a mutant where a particular statement is removed or deleted, we have to cover that statement in the original program, right? So if we achieve a higher mutation coverage in this case, we are actually covering that statement, and so that's why mutation coverage can subsume statement coverage, and it can also subsume branch coverage. So what we can do is consider an extreme case. We can replace all the predicates used in the conditions with a constant true or false. So to kill a mutant where predicate is set to true, a test case must be able to cover the false branch in the original program. And reversely, it is also true. If we set all the predicates to false, then the test case must be able to cover the true branch of the original program to kill this mutant. So this is branch coverage. So mutation coverage can actually subsume branch coverage as well. And there are many more practical considerations. And mutation testing is indeed expensive. Just now you asked actually this question here. So we can do a lot of mutations because we can do a small change to the program to create a mutant. And we can create a lot of mutants for a program. And we must run all the tests against all the mutants. So this is very expensive. And typically we have to generate many mutants because by default we do only one change per mutant by default. And if cost is an issue here, because it depends on it is actually case by case, because if your program is small, then the cost is not a big issue, and if you don't have many test cases, it's also not a big issue here. And if cost is indeed an issue here, we can use weak mutation testing. So weak mutation testing means that we apply multiple mutation operators per mutant. So we do multiple changes in one mutant. And this is called weak because it doesn't help us because we apply multiple changes, and it actually doesn't exactly tells which test case is better, because the test case could be killing the mutant because of only one errors injected, and it may not be able to cover all the errors injected into the mutant. So that's why this is called weak mutation testing. And for weak mutation testing, what we can do is we can seed multiple faults into a single mutant, and this mutant could be called the meta mutant. And then we can divide the program into segments and track the internal states of both the original program and all the mutants when executing a segment of the program. And then we can kill all detected mutants while intermediate states differs instead of waiting for the final execution result. And this actually helps us to decrease the number of test executions. And this is some kind of formal definition of how do we do weak mutation testing and roughly how it works. And let's do an exercise to see how exactly it works. So let's consider the case study of the last question in assignment 1. And what we can do is we use the good test case that can effectively detect the bug here. And let's do a strong or normal mutation testing, and let's do a weak mutation testing. So for strong mutation testing, we need to first execute the test case of the original program with the original program, and these are the edges covered because A is larger than B. So we will go to the first true branch here, and because C is smaller than A here, because if we take the true branch of the first if, the value of time becomes the value of A, and C is smaller than A, so we will take the false branch here, and we will return 4 in this case. We will return 3 in this case. Sorry, there's a typo in this slide. And we need to run this test case with the buggy program. And if we run it with the buggy program, a is not larger than 2 plus 1. So we take the false branch, and temp, the value of temp becomes the value of b. And the value of temp is 2. And c is also 2. 2 is not larger than 2, so we go to the false branch here. And we will return 2. And this captures the bug. We can capture the bug by comparing the return values. And if we do a weak mutation testing, what we can do is, although this is not injecting multiple bugs, but let's just follow the workflow of weak mutation testing in the previous slide. So what we can do is we can execute we need to also execute the test case with the original program, and we will go through exactly the same path here because we are using the same test case. And for the buggy program, once we have reached this basic block, we will notice that the internal state is changed because we can either track which branch we are taking here. We can either track which branch we are taking here. We can also track the value of temp here, because in the execution of the original program, the value of temp when we reached the third basic block is 3. But if we do this, the internal state of temp is changed. The value of temp becomes 2. So we can capture the bug here. So this actually helps us to save some executions, and this actually helps us to detect the bugs earlier. So this is how weak mutation operating works in this example here. Let me fix the typo here. And let's continue. Okay. The last topic today is about mutation. Okay.
Firstly, what do we do with the live? When we have the live mutants that come back to us, what do we do with them?
Oh, that's a very good question, actually. In practice, and actually, I know that there are some companies, small startups, doing auditing for smart contracts. They use mutation testing as well, and they try to kill because their customers are some developers of smart contracts, and they do have their own test cases, their own test suite together with their code. And when they do mutation testing, if they could see there are some live mutants, they need to manually analyze why these mutants are not killed by the test suite, which means that there are some code or some potential issues that the original test suite cannot cover. And then it means that there might be some issues with regard of the code sections or the locations where we apply the mutation operators. So they need to manually analyze this. Yeah.
Is it possible then that you could just get, because we said before that many live mutants could just have the same behavior as the original program.
Yeah.
So is it possible then that you'll just have a whole lot of, let's say you have a max function, right? Like it doesn't matter whether it's a like strictly greater than b or a greater than or equal to b, right? The same sort of thing.
Yeah.
All these sorts of cases that keep the behavior the same will have to be manually checked.
Yes, of course. And for example, if we change C is larger than temp to C is larger than or equal to temp, it makes no difference here actually to the actual behavior of the program, because it will still return the larger value in the end. So in this case, if a mutant, this mutant is not useful, so it's actually hard to to determine whether the semantics of two pieces of code are equal or not. So we have to manually do this normally in practice. We have to normally check for unuseful mutants.
Sorry, just one other question.
Okay, okay.
Also, it seems like there's an assumption that we have, which is that we already have a working program.
Yeah.
We're trying to mutate. So
Yes.
up with that, because like we're trying to test the program to see if it's working, but then now you're assuming it's working.
Oh, yeah. That's actually the competent programmer hypothesis. So we have to assume that there's no requirement level of errors in the implementation in the target program. So it's actually related to this hypothesis of competent programmer. So we have to assume that the target is already built. Yeah.
Why would you want to test it?
We still need to test that, right? We still need to test because even for some commercial products, they are well tested. They still have bugs, so we still need to test if it is already implemented well, right?
It has bugs, but like close enough to correct.
Yeah.
It will still, the live units will still be useful.
Yes.
Okay.
Yeah. We should always assume there are bugs for different software. And you can also assume there are bugs in the specifications of the assignments as well. But I will update them later once you have reported them to me. So let's continue to our last topic today, which is to use mutation testing together with fuzzing. And actually, there are two concepts that are sounds very similar to each other: mutation testing and mutation-based fuzz testing, or mutation-based fuzzing. So in lecture 9, we have learned that fuzzing could be either mutation-based or generation-based. And I hope you can still remember what is a generation-based fuzzer. And sometimes in many people, even if they have worked for many years or they have been in academia for many years, they may mix up the concepts of mutation-based testing and mutation testing. So the names are similar, but the concepts are totally different, because mutation testing is to modify the target program to evaluate test cases. The purpose is to evaluate the quality of test cases for mutation testing. And for mutation-based fuzzing, the mutators are used to create new test cases. So these concepts are totally different. And we can actually use mutation testing to evaluate the performance of fuzzing, the fuzz testing. So there's actually a research paper, and this paper is about using mutation testing to evaluate fuzzing. And you can see that there's a blue edge in this screenshot, which means that there's a link. You can click on this link to access the paper. And there's they have a GitHub repository storing this benchmark created by them. And actually, Google is now using this benchmark for their fuzzer computation. And but I found that I was considering using this for assignment tool to evaluate the fuzzer you have created, and because this will, to make sure that assignment tool can echo some of the content we have taught in the lecture. But I found that this repository is very hard to use, and because this paper was published like 3 or 4 years ago, and the environment is totally different. The dependencies are quite old. Just like AFL, you may have to install an older version of LLVM to use the LLVM path instrumentation. So it's hard to use, and we give it up. But this paper is still useful because it documents all the mutation operators it used to modify the C code. And you can see that they have many different mutation operators, which are called patterns here. And for example, they can mutate all malloc calls to achieve buffer overflow or out of bound errors. This is very close to some real mistakes made by developers. So you can have a look at the design of all these mutation operators and observe how the design reflects real faults made by the programmers. So the closer the mutations or the faults we could inject to real faults, the more likely that the mutants are useful. So you can have a look at this if you are interested, and don't mix up the concepts of mutation testing and mutation-based testing or mutation-based fuzzing. So they are totally different. And that's all about today's content. And let's have a quick recap, and then let's have a look at the assignment 2 material. So let's have a recap for today's content. So first, we had an overview, and we started from looking at the example of assignment 1. Actually, the open-ended question is asking you to manually do a mutation testing to evaluate the quality of the test cases. So that means that some test cases are indeed better than others, and how could we evaluate the test cases? And the method of evaluating test cases is to modify the target program to evaluate test case. So to modify the target program and evaluate test case, and this process is actually called mutation testing. And the key concept in mutation testing is called, one of the key concepts is called mutant. So a mutant is actually a modified program with small changes. And the mutant is killed if it fails any of the tests that could pass the original program. That the original program could pass the test, but the mutant cannot pass. Then the mutant is killed. And if a mutant is not killed by any of the test cases in the test suite, then it is called a live mutant. And we can also calculate the mutation score according to the number of killed mutants divided by all the mutants. And this actually reflects the quality of the test suite. And we learned many different mutation operators, from expression level to operator operand level to statement level, and to some all related mutation operators. And then we learned about how do we conduct mutation testing. We learned the workflow. We also learned two hypotheses which must be satisfied if we want to apply mutation testing, right? And we also learned that in practice, mutation testing could be very costly. So we can do weak mutation testing to inject multiple bugs in one program and to check the internal states of the program to capture errors. And lastly, we emphasized the difference between mutation-based testing and mutation testing. Actually, mutation testing could be used to evaluate other testing techniques. So that's all about the contents of mutation testing. And let's have a look at the material of assignment 2. So this is the total mark of assignment 2 is 60% of the course. It's like a final exam for many courses. Like some courses, the final exam is 60%. So you can imagine it as a take-home big coding exam. And I'm pretty sure that I'm not very sure if large language model can help you to code this. But you may need to do some prompt engineering if you really want to use large language model to solve the problem for you. But by default, I don't think it can code it correctly. So there are actually the task is mainly about building a gray box fuzzer, which is similar to American fuzzy lob. And when building this fuzzer, you may want to apply some of the knowledge you have learned during the lectures, and I have implemented the key structures for you. So basically, we have learned about the fork solver and shared memory in lecture 10, and those are actually already implemented for you to start with. So the code you can get is actually a runnable fuzzer, which can do some dummy mutations, some very simple random mutations, and execute the target program and check the status code returned by the target program. And it has a small chance of detecting bugs in the programs, but it's definitely not a good fuzzer. And your task is to implement some advanced features based on this small framework, and you have to code in Python here. It should be easier than coding in C or C++, so it should be easier. And you have two targets for testing here. The first one is MJS. I think it's no longer maintained, but it was a popular fuzzing target because it has a lot of vulnerabilities, and it's created by a small company, and it is a small JavaScript engine used for IoT devices. So it is very buggy. We are using a buggy version of this MJS, and it has a lot of vulnerabilities. So basically, you can try to use this target to see if your fuzzer can detect bugs or not. And the other one is called CJSON. You can see that it has many more stars on GitHub. Actually, it is considered one of the most popular JSON parser nowadays. A lot of JSON parsers are powered by this library here. So you may see some JSON parsers in Java or in Python. Actually, they are relying on some C libraries behind, and the library behind is CJSON. It is actually, you can see that it has its own fuzzing folder in this official repository. It is actually, the author is actively fuzzing the project himself, and it is delegated to Google's OSS Fuzz project. So Google is actually helping these open source projects to do fuzzing, and so it is very robust. It's not very likely that you can find a vulnerability inside this target. But if you can find a bug, if you somehow you find a bug, and then you can tell us, you can report it on the forum, and we can give you some bonus marks for the new bugs you have detected. And that's all about the fuzzer framework and the targets. And for the source code, you can access the source code here. So all of them are Python, and you can run this fuzzer in this Docker environment. You can pull the image and you can run this. And here is the file structure of the Docker, and this is a command to run fuzzing. And you can actually, once you have set up the Docker image, the Docker container, you can already run this in Docker, and you can see how it is running. And And here are the features you have to implement. And I suggest that you follow the order to implement the features. Although the first one is a little bit harder than the second one, but I still suggest you to follow this order, because it's like you are completing the functionality of this gray box further according to this sequence. So the feature one, what you need to do is actually the default implementation. It is a very weak implementation. It cannot. It is more like a black box further, because it doesn't actually use the feedback. It collects the feedback, but it doesn't make use of the feedback. So we need to keep, if a new test input can cover new branches or new basic block transitions, then it should be kept as a seed in the queue, and it should be used again when we do fuzzing. So this is actually somehow similar to a genetic algorithm. We will learn genetic algorithm next week, but this is somehow similar to this genetic algorithm, and you need to implement this feature to make it a true gray box further, to make use of the feedback, to keep test cases as seeds. And there are some hints here. And the second one is this current implementation can report bugs, but it doesn't keep the test inputs that can trigger the program to crash as proof of concepts. So one advantage of testing is that we can keep the test inputs that can trigger the program to crash as an evidence that the program has a bug, and it also can help the developers to debug. So if we do static analysis, we don't have this advantage, because we don't really have an actual concrete test input to reach the bug. So this is the advantage. So you should be able to save the crash, the test input that causes the crash. And this is relatively simpler. And the third feature is, remember in our lecture 10 we have discussed some decision points, some decisions that we must do during gray box fuzzing. One of them is that given a queue of seed input, the first decision we need to do is which seed should we select to create new test cases. So this seed prioritization actually helps to determine which seed to be used next. And what you need to implement is the favored calculation of AFL, similar to AFL, and you can find the algorithm here in lecture 10, and there are many links in this specification. You can click on them and try to grab some useful information. So the seed is like this. So you should maintain a dictionary where the keys are basic block transitions, the indexes in the tree space or in the shared memory, and the value is a list of seeds that can reach or cover that particular index. Once you have this, you should sort all the lists according to execution time times the file size. So the smaller the better. And then you mark the first seed in every list as favored. So the algorithm is clear in plain text, and you have to implement it in a programming language. And how it works is that if there's because the fuzzer will go through the queue of seeds one by one, and once it visits a seed, and if there are favored seeds that hasn't been used in this round of testing yet, then it should skip that seed and until it finds a favorite seed in the queue. So this is how it should work. And feature 4 is about power scheduling. This is happening. This is the decision we need to do after we have selected the seed. So we need to determine how many new test cases should we generate based on the new seed. So we need to calculate a score for every seed, and you can do a very you should make use of the coverage, like how many basic block transitions have been covered by this seed and the execution time of the seed to calculate a score, and then use the score to determine the number of new test cases to be generated based on this seed. So basically, maybe what you can do is you can just follow the original implementation of AFL and do it. So maybe if the score is 1,000, you can use 1,000 to divide it by 100, and as the actual number of the new test inputs that should be created. So you should create 10 new test inputs in this case. So this is power scheduling. And then we need to, after you have done all this, it is a workable gray box further, and you have to enhance it by enhancing the mutation operators to create better new test cases. And you can try out the havoc. You can try to finish the mutation operator, because the current mutation operator in this implementation is a very dummy one. It just randomly selects a byte in the file, in the seed, and then flip certain bits from 0 to 1 or from 1 to 0. So this is very, very simple, and you should implement the mutation operators here into this havoc mutation. And then you should also try to implement the splice mutation operator, because the algorithm of American fuzzy loop is essentially a genetic algorithm, and we will learn that later next week. But for genetic algorithm, there's a mutation operator called crossover. So which means that we are trying to combine two test cases into one test case, and this is done by using the first half of the first test case and the second half of the second test case and combine them together into a new one. So this is called crossover or splice mutator. So you have to implement this, and if you can successfully implement feature 5, this should be relatively easy for you to do. And for feature 5 and 6, you do have some small bonuses for you if you can implement some more advanced features. So for feature 5, if you can implement the dictionary-based mutation, because as you see, the two targets are, one of them is a JavaScript interpreter, so it accepts JavaScript files as inputs, and the other one is a JSON parser. It accepts JSON files as inputs, and both inputs are well structured. So you could use dictionaries, and you can see that AFL actually provides dictionaries for JavaScript and JSON. You can see this. You can somehow create a dictionary-based mutation. So, and there are some more descriptions here. You can follow them to get the bonus mark, but the total mark won't exceed 60 if you can earn all the bonuses and earn a very high score. And for feature 6, you also have one bonus feature, and I will add more details once we finish the lectures in week 9. So about this bonus feature. So we we need, because because after you have implemented feature 6, you will have 2 mutation operators, or maybe even more mutation operators if you want. And the thing is, we have to have some strategy to select which mutation operator to use. And the selection of mutation operator to use could be modeled as a multi-armed bandit problem. Multi-armed bandit problem is actually a very famous problem in reinforcement learning. And have you heard about the bandit machine? No. Okay, it's somehow related to gambling, but we will learn that later next week as well. So you can try to implement multi-armed bandit strategy. This is the easiest one, this epsilon greedy strategy, and to earn this bonus mark. And we do have a bonus feature as well. So feature 7 is a bonus feature. So we have a lot of bonuses for this assignment, and because the major content is what has been taught before week 7, and the bonus content are more like the contents to be taught in week 8, week 9. So in this is actually the default fast driver maintained by the developer of CJSON, and you can see that the initial seed file of this fast driver is not really a JSON file. It actually uses the first 4 bytes of the input file to select options to be used when testing the JSON parser. So this parser actually parse with options. It actually parse the JSON file with some options. So this is the actual JSON data, and there are some options to be used. So what you can do is you can see there are some options that could be used in this file, and it actually uses the first 4 bytes in the original input in the test input to determine to turn on and turn off these options. So, but if we just use the default mutation operators, we are actually not systematically testing the combinations of these options. And to test combinations of operations effectively, we have to use some concepts in combinatorial testing, and we will teach it in Thursday this week. And you can test the combination of options. You can try to implement a pairwise or two-wise combinatorial testing for these options in this CJSON file. And you have to make it. You have to implement some utility features as well, because this mutation operator is not useful for MJS, because MJS doesn't have these options. So you have to make it. You have to modify how the program passes the configuration file to read these options. So this is roughly the assignment 2, and you will need to submit it by the end of week 11. So you have 4 weeks to implement it, and don't do it in the last week. Although it is doable, I think, for most of you, but don't do it like this. You should try it earlier, because you may encounter many corner case bugs or some tricky things. So it's better to start early. And that's it for today's lecture. And thank you for coming.
How many hours do you think it'll take to complete, like a time estimate? You said like a week, but how many hours do you think? Like 40 hours?
I can't estimate how many hours you need, but it depends on your understanding and skill and so on. And you are encouraged to use large language model to code this, because in real life you are in many companies they now use coding copilots when they do the development, and it's an advantage if you can master the usage of large language models. But I don't think you can easily use it to generate the correct code here. So you have to try. Okay.
我那个中午下午可以过来找你聊一下那 thesis 的事。
行，你明天啥时候？
什么？
明天啥时候
？3点左右。
行。
或者2点我都可以。那2点吧。
好。
好。
Is there feedback for the song? Sorry?
You can send us an email for details.
Is your email, is it on web CMS?
Yes.
Not here on the forum.
One other question about, yeah, sorry, I keep having questions when it came to this, but it's, so for mutation testing, you don't need a test article because you're already assuming the program is working, right? So you actually, so when you say you have a test suite, you're not actually talking about the test article, you're talking about the test cases only.
Yeah.
Right? Okay, that's pretty handy.
Because for test cases, normally, for example, for the testing assignment one, you can check maybe for the test article, we can use a certain of the return value to be sure.
But it seems that you don't even need the test article. Like you can use the test article for visual test, but when you're doing a section thing, right?
Yeah.
You're using the program.
For weak mutation testing, we don't even need the test article because we are checking the inconsistencies between the animals. And this is somehow similar to the concept of differential testing.
Right. I assume that's like you have like two things.
Yeah,
and like
comparing full work and so on.
yes, I did that once.
Yeah.
It was interesting. It was really bad.
Why that's why?
I was trying, so I had this reference implementation of a particular algorithm, and I was trying to like optimize it to make it faster. But then I tried tracking all the internal state to check if it's the same, but I ended up changing the internal state, so the test didn't even work.
I see. Yeah. Actually mapping the internal state is quite tricky.
Because especially in the, like when you're talking about the section testing, you kind of need to be choosing some mutation operators that you're using and then excluding others.
Yeah.
For example, if your internal state counts as like which branch you're going down, you can't change the structure of the program.
Yes, of course. So I actually omitted that detail closely here because it's very complex. So some mutation operators may restructure the entire code, like revision, if they need some condition value if that happens, then we can hardly match the methods. So
you have to be kind of very intentional about it.
I have to select
I see.
written in Python, but it heavily depends on exe. So it invokes exe functions with Python code.
Yeah.
So it's roughly half function.
Okay. And Python environment doesn't manage too much, right?
That's because you can use developer and you don't have to install it.
Oh, no. Okay. I was going to use Python 12 because I can't stand untyped Python.
No, I'm not using that feature.
Okay. Well, I'll have it. But it's, if I use a different environment, we're not gonna like. It's not, is it gonna like?
The default version of Python installed in Docker is 3.7.
But when we submit it, oh, okay, that's fine. If I submit it,
I haven't released the submission yet, but we will
okay,
see how it is.
okay. I guess I'll use 3.10 for now, just to be safe.
Yeah, sure.
All right. Okay.
Okay.
Thanks.
Thank you. See you.
那个女生那个她可能图画对了，我们也给她加上这个版本是个女生啊，那个是挺好的。她那个给加上去。但我是不公布了，就是她的岗位人家对啊，那一般都是那个虽然说我觉得是会发那个前面那一块儿，就是前面那个 C 和 E 不会有其他的。
但是你因为有的人说是你就是
对，
但是你把
我那个图是，如果我是合在一起画的，我那个图也都是合在一起的。如果我是分开，就都是分开。我想看最开始那个图我也说，分开一个就分开，合在一起就合在一起。那个人他是不卡 system 的，而且卡就是发现我觉得那卡 system
我觉得这个图是不是要改？